Hello everyone, and thank you very much for the invitation to give this talk. My name is Andrew McPherson, and I'm joining you today in two different capacities. First, I'm an academic in the Centre for Digital Music at Queen Mary University of London, where I lead a group called the Augmented Instruments Laboratory. We're a team of 12 researchers who focus on designing digital musical instruments, studying performer-instrument interaction, and creating embedded hardware systems for real-time audio. You can find more information on the lab and its projects on its website, instrumentslab.org. Bela is a spin-out of the Augmented Instruments Lab, and I'll tell you about a couple related lab research projects as we go along. Second, I'm a founder of the company Augmented Instruments Limited, which produces Bela and supports its growing community of makers, artists, and researchers. There are currently 5 core members of the Bela team, plus a wide network of collaborators around the world. So let's jump right in. As the title says, Bela is an embedded hardware platform which is capable of extremely low audio latency. Now personally, I'm obsessed with latency, and by the end of this talk I hope I'll also convince you why low latency is so critically important. I'll explain where latency comes from and the things that we can do about it. After that background, I'll introduce Bela in more technical detail. Bela brings 3 important things to the table. First, it's an embedded computing platform designed with interactive audio in mind. It has the power of a single-board Linux computer with the connectivity of microcontroller boards like Arduino, and of course its signature feature is an action-to-sound latency under 1 millisecond. Beyond that, Bela also introduces a new approach to working with sensor data, where all the analog and digital channels are treated like audio signals, sampled with high bandwidth and high timing precision. Finally, the entire platform is open source, both hardware and software, and we maintain a growing array of community resources. Now this talk is going to be divided into 4 parts. First, I'll introduce the theory behind latency in digital audio systems and explain why it matters. Then I'll cover the core technology behind Bela, followed by its user-facing features and community resources. Finally, I'll present a short showcase of a few projects made with Bela, both internal to my lab at Queen Mary and in the wider community. Alright, so let's back up to the beginning. What do we mean by latency? Well, latency is essentially the delay between action and reaction. In this example here, we'll see a sensor input and some audio synthesized in response. The delay between these signals is defined as the latency. Now, this is a fundamental property of every digital system, and the question is why? Well, let's look at what a digital audio processing system actually does. Suppose that we have an audio input signal, which is going to be composed of a series of samples over time. Then suppose that our system is processing that input signal to generate a new output signal. If we are running in real time, then this system has 2 mandatory requirements. First, for every single sample, the computation of the output needs to finish in bounded time. An output sample that's computed after we were supposed to play it is totally useless. Now, how long it takes to generate that result is up to us, but the point is that there needs to be some fixed delay that we can guarantee will never be exceeded for any sample that we compute. That delay will end up determining our latency. Second, to run in real time, then on average, processing one sample can take no longer than 1 sample period. If that's not the case, then you can see that we would systematically fall behind because we can't process the data fast enough as it comes in. So these are our 2 requirements, one that applies to every single sample, and one that applies on average over time. And just to underline this point, a real-time audio system is only as good as its worst case. We don't tolerate audio dropouts during a live performance, therefore a system that only meets 99% of its deadlines is simply not good enough. Now on this basis, how do we decide where we set our latency? Obviously, we want it to be as small as possible consistent with this principle. So let's ask, how often do we need to calculate a new sample of our audio signal? Suppose that our audio is running at 44.1 kHz. That means we need a new sample 44,100 times per second, which works out to every 22.7 microseconds. Now, potentially, we could just have our computer run a bit of code every time we need a sample, as a sort of just-in-time calculation. This is a compelling idea, but there's a big problem that makes it unworkable. The problem is that any computer is going to be running lots of different processes all at the same time, and there's no way we can guarantee that we'll react quickly enough to generate a new sample every 22 microseconds, no matter how simple our audio calculations might be. Therefore, what we're going to do instead is process our audio in blocks. We gather together a group of audio samples, and only once that whole group is ready do we process it. What this gives us is that the audio hardware can be busy playing one block while the processor is calculating the next one, sort of like this. And again, remember that each of these blocks contains several samples. The other big advantage of block-based processing is that we don't need to run our audio code nearly so often. We can always plan our calculations up to one block in advance, which lets us tolerate more timing uncertainty from the rest of the system. For example, if our block contained 5 milliseconds worth of audio samples, and it took only 1 millisecond to actually run the computations on it, then we can handle a reaction time of up to 4 milliseconds from the operating system before our audio code needs to run. Now this is very useful, but of course it comes with a price. The price naturally is latency. The larger the block size, the longer the delay between the input and the output. Now we can be more specific about how long that latency is by looking at what the system is actually doing. We have three things happening at once. First, the audio input hardware is filling up a block of samples. When it's full, this block gets passed to the CPU to do our audio processing, while meanwhile the input hardware is filling up the next block. Once the CPU is finished processing a block, then that one gets played through the audio output hardware. Meanwhile, the CPU is working on the next block, and the audio input is filling up the one after that. So again, at any given time there are three things happening in parallel: input, processing, and output. And notice that even if the processing we're doing is extremely simple, there's always a latency of exactly twice the block size for a sample to make its way through this particular pipeline. There's one other term that we should define, and that is jitter. In a simple audio processing system, the round-trip latency is usually a constant, meaning it's the same for every single audio sample. But if we have an interactive audio system, where audio is being generated in response to other sensors, then we could have some asynchrony between our sensors and audio, with data coming in on different threads. So here, suppose we're processing audio in blocks, and we have some sort of trigger coming in from a sensor, which could arrive at any time. Our goal will be to synthesize audio in reaction to this trigger. Now what happens in practice is that it can be hard to work out when within each block the trigger came in, so often the best we can do is to generate audio at the beginning of the next block. The net result is that we have an inconsistent reaction time to each of these triggers, which produces our jitter. The implication here is that the larger the audio block size we have, the larger the potential amount of jitter. So now let's put these pieces together. In a real-time audio system, we have three main sources of latency. First, there is some inherent latency in the analog-to-digital and digital-to-analog converters themselves, especially if we're using the sigma-delta style of conversion used in audio codecs. The reason is that a sigma-delta converter internally contains a small digital filter as part of the conversion process, and that filter introduces some latency. The latency from these converters is totally independent of the processor or the operating system, and the only things you can do about it is to either increase the sample rate or choose a different chip. On Bela, this latency adds up to about 850 microseconds round trip. Next, we have the latency introduced by the buffering, which we just saw. This is a function of the operating system and the audio architecture, and the latency scales linearly with the block size. It could be anywhere from under 1 millisecond to potentially 20 milliseconds or more, and is often the most significant source of latency in a real-time audio system. Finally, we can't forget that our audio code itself might introduce latency. Typically here, we might be talking about the group delay of filters, which is a mathematical property and not something that can be solved with a faster processor. And this delay can become especially significant if our code involves any block-based processes, like a phase vocoder using FFTs. Remember then that to find our total audio latency, we have to add all of these sources of delay together. But actually, we're often interested in building interactive systems, not just audio processing, but potentially generating audio in response to some kind of user input captured with sensors. Here, let's have a look at a typical configuration used by makers and researchers, where we have a microcontroller board like an Arduino connected to a computer running sound-producing software like Max or PD. In this setup, we have 4 different sources of latency. First, we have latency associated with the sampling period of the sensors. Often with a microcontroller, we'll sample our sensors at a relatively low sample rate, and so the sampling period can be a significant source of latency. We then have latency from the communication link between the microcontroller and the computer, particularly if this involves USB or serial. On full-speed USB, packets are transmitted every 1 millisecond, so we should add at least that much latency. If there's also a hardware serial port involved, then the bitrate of that port can become a driver of latency. For example, if we're working at 9600 bps, which inexplicably still seems to be used in a lot of the Arduino example materials, it can take 1 millisecond just to transmit a single byte. A more consequential but often unpredictable source of latency is the operating system driver. Drivers for serial ports are typically optimized for data integrity and not for latency, so they make no guarantees on how long it will take for a byte to be received. The net result is often a situation where most data is received right away, but occasionally and unpredictably, some bytes can take tens or even hundreds of milliseconds to come through. This, of course, can wreak havoc with real-time guarantees for audio. Finally, if we're generating sound in response to sensor data, then we still have at least half the audio chain to contend with. And remember, it's the sum total of all of these factors that we care about. Now you might reasonably ask, does any of this even matter? And the answer is emphatically yes. It matters a lot more than you might think. For very long latencies, 50 milliseconds or more, you might hear an audible delay. But even when you don't perceive a delay, latency can degrade the perceived experience of an interaction, especially for musical instruments. The digital music pioneer David Wessel proposed that instruments should have no more than 10 milliseconds of latency and no more than 1 millisecond of jitter, and this has been an accepted standard in the community for some time. However, in Wessel and Wright's paper, they don't say where this figure comes from, so we set out to test it in a controlled study. We built a simple hand percussion instrument using Bela, based on a set of ceramic tiles that are played with fingers. The instrument triggered gamelan sounds, and we designed it so that we could adjust its latency. We compared 4 settings in a double-blind A/B test to measure both the experience of the performers and the timing accuracy of their performances. Here's an example of that instrument in action. What we found was pretty clear. For both professional percussionists and amateur musicians, we found a significant reduction in rated quality of experience with both 20 milliseconds of latency and 10 milliseconds of latency with 3 milliseconds of jitter. However, the condition with 10 milliseconds of latency and no jitter was effectively rated equal to the no latency reference. Alright then, so how do commonly used maker and research tools stack up against this 10 millisecond threshold? Again, we can look at the common approach of using a microcontroller board connected to some sensors, which is communicating with a computer running a program like MaxMSP or PD. We conducted a systematic test of this arrangement, amongst others, and found that many of the commonly used configurations have absolutely terrible latency performance, often above 10 milliseconds and with considerable jitter, because of the factors that we've discussed previously. Let's dig into the source of jitter a little bit more. In this example, we have an Arduino attached to a computer by USB, and we're running audio software with a block size of 128 samples or 2.9 milliseconds. We can plot a histogram of the reaction time to 1,000 successive events, and what we see here is a very strong jitter at the interval of the block size, exactly like we would have expected. By contrast then, here is Bela, plotted for different block sizes and sample rates. Notice the change in x-axis. Every configuration here is substantially under 10 milliseconds of latency, and in some cases, from analog in to analog out, we can get reaction times as low as 100 microseconds. So how does this work? Let's now have a look at the technology behind Bela. Bela is based on a BeagleBone Black single-board computer, which has a 1 GHz ARM Cortex-A8 processor. It also has something called a PRU, or Programmable Real-Time Unit, which is significant for reasons we'll come back to shortly. The Bela hardware also includes an expansion board with stereo audio input and output and 16-bit DC-coupled analog I/O. Here you can see an overview of the kinds of connectivity available on Bela. You can also use the standard interfaces on the BeagleBone, like USB and Ethernet. We've also made a scaled-down version called Bela Mini, which has the same processing capability but in a package 1/3 the size, with most of the same I/O except for the analog outputs and speaker amps. Electrically, the audio and the analog converters are connected to the CPU by I2S and SPI, both of which are high-speed serial buses. Now the Linux kernel has drivers for these buses, but on Bela we cannot use these drivers. The reason is the latency issue that we saw before. The kernel handles many different tasks simultaneously, and we simply can't guarantee that it will react fast enough to new samples of data coming in. So here's what we do instead. Bela uses a real-time extension of the Linux kernel called Xenomi, which lets specified tasks bypass the kernel entirely and effectively go straight to the hardware. This means that we can guarantee that those tasks always have the highest priority on the board, no matter what else might be happening. We've written custom hardware drivers for the audio, analog, and digital I/O which bypass the kernel this way. But what's really great about Xenomi is that our code can also still transparently access everything else that Linux provides, like storage, network, and USB devices. The upshot of all of this is that Bela is capable of running with far smaller audio block sizes than conventional systems, even down to just 2 samples. As we saw previously, audio buffering is the main latency driver in most systems, so what this leaves us with is mainly the latency inherent to the audio codec itself. That means we can get down to about 1 millisecond round trip from audio in to audio out, or if we use the analog converters that are not sigma delta converters, we can get down to 100 microseconds. Now I've glossed over an important detail here, which is how the audio and analog samples get collected into blocks in the first place. Even Xenomi is not fast enough to react to every single sample as it comes in. So here we turn to the programmable real-time units on the BeagleBone. These are extremely useful microcontrollers which are optimized for timing-sensitive tasks. They have access to all the same memory and peripherals as the CPU, so on Bela, we use the PRU to bundle the audio and sensor data together into a block, put it into a buffer in memory, and then pass it over to the CPU where it's processed. Once the processing is finished, the buffer is passed back to the PRU, which sends the results back to the hardware. Alright, so at this point we've gone fairly deep into the weeds of interfaces and protocols. But I want to highlight that this PRU architecture also has a really useful user-facing implication for the interactive systems that we build, which is that all of the audio and sensor channels are sampled synchronously aligned on a sample-by-sample basis. Effectively, the analog and digital I/Os act as extra audio channels, and this is exciting for a few different reasons. First, it nearly completely eliminates action-to-sound jitter because each channel is aligned on a sample-by-sample basis. Second, it lets us easily apply audio DSP technique like filters and FFTs to sensor data. And finally, and most significantly, it means that every sensor channel provides data as rich and nuanced as the audio itself, which lets us build systems with real subtlety of interaction. Let me give you an example of that. This is a simplified guitar-like instrument which we call Strummy. We built Strummy as a research probe around the cultural factors of digital musical instruments. In the paper referenced here, we asked a question about whether greater richness of control produces a better musical instrument. To do that, we built 2 versions of the Strummy. Each one of them has 6 short lengths of string with piezo pickups, with each string driving a simple Karplus-Strong synthesis model that can be tuned to different frequencies using a set of chord selection buttons. In the first version of this instrument, we implement a peak detection algorithm on the piezo signals, such that, when the string is plucked, a trigger is sent into the string model. In the second version of the instrument, the audio signal from the piezo drives the string synthesis model directly. It's probably easiest to explain this by way of a video. We gave both versions of this instrument to 16 guitarists and 16 non-musicians and asked them to rate which setting they preferred. The results were interesting. Guitarists uniformly preferred the audio-driven model. They commented on its richness and on its relationship to familiar guitar technique. On the other hand, the non-musicians were more evenly divided. Some of them found the simplicity and the uniformity of the sample trigger sound easier to play. but it's worth emphasizing that being able to have this richness of interaction at all is a function of the high bandwidth, low latency sensing that Bela provides. The last point that I'll make about the Bela technology relates to its user interface. Setting up a toolchain for an embedded device can be slow and frustrating, so we've made a friendly browser-based IDE that lets you get started coding right away. The IDE also includes a suite of example materials, an interactive pin diagram, and a built-in oscilloscope that lets you visualize your signals. Bela supports several programming languages, including C++, PD, SuperCollider, and Csound. Support for the latter two languages has been contributed by members of the Bela community. And on that note, I'll now switch to talking more about Bela as a community platform rather than just a technical device. Here it helps to start with some history. Bela didn't start out as a general-purpose platform. It actually started as a specific musical instrument called the D-Box, which I and Victor Zappi made in 2014 as part of a study of the creative misuse of technology. After those initial studies, my lab started using the underlying hardware for other research projects, and we also used it as the basis for a class on real-time signal processing. As we adapted it for more general use, members of the lab also added new features like the browser-based IDE. At the same time, we also built up a network of several dozen external collaborators in London and around the world, and we gave a series of workshops on the technology. On that basis, in 2016, we decided to launch Bela to the public on Kickstarter. We were only seeking to raise a small amount of funding, but we ended up tripling our goal on the first day, and in the end raised over £50,000 from over 500 backers. In this paper at Chi, I and my co-authors reflected on this community building process around Bela, as well as having a detailed look at a specific workshop we ran at the Stime Center in Amsterdam. The figure here charts the growth of the Bela community over the early years of its development. Now the community stands at thousands of members who are making cool projects and contributing features back to the platform. As I mentioned before, Bela is now maintained by a spin-out company which we founded after the Kickstarter campaign. We still have strong ties to the university, but also more independence to develop the Bela community and to diversify our product line. Here's a sampling of some of the resources that we've made available to the community. First of all, Bela is entirely open source. You can find all of the hardware designs and all of the software on our GitHub repository. We also maintain a knowledge base, which is a focal point for tutorials, getting started guides, and technical information. As an example, the knowledge base has a detailed tutorial on PD audio programming with Bela. Starting last year, I've also been producing a free YouTube course on audio programming in C++. You can find these videos on our YouTube channel, and there are companion materials for each lecture on GitHub, and this includes slides, code examples, and links for further reading. Just as an example, one of the lectures covers latency in considerably more detail than I've presented in this talk here. We maintain an online forum where Bela users can get support on their projects, and we have a blog which features some of the cool projects that have been made by the Bela community. And that brings us to the final section of this talk, where I'd like to show you a few of those projects made with Bela that might be of particular relevance to the ICAD community. First is a project in my lab by Charlotte Nordmoen and collaborators working with e-textiles and other craft materials. We created a magnetic sensing technology which generates a signal when a conductive material moves in relation to a permanent magnet. Now, in one sense, that's exactly how every magnetic pickup works, but we have a few tricks to increase its sensitivity and flexibility, which are described in the paper. But most importantly, the sensor technology was decontextualized, presented to participants in a workshop where they made their own sensors from conductive and non-conductive materials. We created a deliberately minimalist sonification of the sensor signal, using it to modulate the amplitude of a sine wave. I'm going to play a video of this in just a minute, but I want to call your attention to just how much detail you can hear in the manipulation of these objects, even with such a simple sonification. For example, plucking and squeezing objects produce subtly different sounds that you can hear. All of this works because of Bela's low-latency, high-bandwidth sensing. Now, what I want to propose for ICAD is the value of these subtle auditory cues as a means of conveying information. And in the paper, we also talk about the process by which participants made meaning of an unfamiliar material through this sonic interaction. The next Bela project from my lab is by Laurel Pardew and collaborators. It's called the Swamplin. It's a kind of hybrid violin where the violin body is acoustically decoupled from its strings. We use an electric violin with custom pickups on each string, which employ a similar sensor technology to the previous project. The signals are processed by Bela and ultimately fed to vibration transducers in the acoustic body. That means that the sound is ultimately localized within the violin as usual, but it can also be manipulated or transformed, for example to change pitch or timbre. Again, low latency is crucial to making this experience believable. Now I'll look at a few projects made by other members of the Bela community. This is just a small sampling of the projects featured on the blog, and in each case I'll mostly let the project speak for itself through the creator's video. First, we have Oral Fabric by Alessia Milo, which is an interactive map made with e-textiles. What you see here is a map of Greenwich in London, where each building will play field recordings from the area when it's touched. Let's watch a video of this. Next, we have Sonic Tree by Daniel Mashkovich. This is a 16-channel sound installation based on audio contact mic sensing and neural networks.
Sonic Tree is a metallic structure in a room of concrete, contrasting with the organic movements it incarnates. Its virtual neuron cells exchange electric signals, and its metallic cells propagate sound faster than in the air. Just like any tree, it offers a comforting shelter with the sounds of insects and the soft breeze in its leaves. The sound installation features an autonomous audio-dedicated programmable processor containing the algorithms for the real-time processing of audio signals. This processor allows controlling 16 independent channels, each of them driving 16 small active speakers distributed alongside the branches of the tree. A small piezoelectric contact microphone placed at the top of the trunk allows amplifying the sounds produced by the movements of the metallic chains. An artificial neural network has been implemented with 16 neurons, each of them corresponding to one audio channel. The signal emitted by each neuron results from a matrix combination which coefficients reflect the sound interactions in the network. The original sound source comes from the contact microphone, and is processed by the neuron network for an effect of an organic movement through the branches of the tree.
Continuing on the theme of large-scale installations, we have Scatter by John Ferguson and colleagues. This is a series of solar power rotating sound sculptures which were created for a festival in Brisbane. The physical motion of each sculpture creates interesting sonic effects through the Doppler effect and through the changing directionality of the sound. Finally, we have Celestial Harmonies by Alberto Novello. In a sense, this is a quite literal auditory display, in that the audio signals you hear are also used to drive the XY axes of a vector graphics display, which creates a tight cross-modal coupling. And with that, I'll wrap things up. There are many more projects to see on the Bela blog. You can find us on social media at Bela Platform, and you can find our contact details and other resources from the knowledge base. If you're interested to get started with Bela yourself, you can get a 10% discount on our shop using the code ICAD 2021. But, of course, this whole platform is open source, so feel free to go check out our designs and remix and extend them for yourself. Beyond Bela, you can find more information on research in the Augmented Instruments Lab at its website, instrumentslab.org. Thanks very much for your time and attention.
Thank you, Andrew. That was fascinating. Jim, could you bring me up as well?
Right.
Hold on.
Bring up Paul as well.
Yeah. Oh, there we go. There we go. Fantastic. So, first of all, congratulations. This is late Sunday afternoon for me, and I'm still awake.
I'm still awake too,
yeah. This is not normally a period where I'm known to be awake. So fantastic. That was really, really interesting. There's a couple of questions in the Q&A, but there's one I want to ask first, and it kind of leads into some of these. So for those of us who aren't familiar with Bela, who haven't actually used it yet, and I'm sure there's some in the audience, myself included, if I got you correctly, you've got this, on the schematic, you had the inputs coming into Bela, and then you've got the audio code bypasses the main Linux kernel so that it's running in hard real time, as you said. What is that audio code that's running there? And that's on the Bela platform, is it?
Yeah, that's right. So, ultimately Bela is designed to replace the need for your computer and for any kind of external microcontrollers, and it basically puts everything into one package. So you have it plugged into your computer so that you can put the code onto the board, and then it's just going to disconnect, and you can power it from a battery. It can boot up straight away and just run your code. So what that audio code is, well, that's entirely up to you, really. You can, it'll come up with a blank window, which of course is the hardest thing to write any code into. But for that reason, we've got a fairly large and growing library of examples and tutorials as well. And so, I find on Bela, as with a lot of other kind of music and maker platforms, a lot of stuff is made by kind of remixing and combining and extending demo materials, and we're really enthusiastic about that. I mean, the stuff is there to be used.
Right. So, okay, I think I've still got in my head this sort of Arduino do, for grabbing the data from the real world, from grabbing the sound. So then you do your processing on the computer, and then you shunt it back out somewhere. But you've actually encapsulated it all down
Exactly.
onto the Bela. Yeah.
Exactly. And so that's why you see in some of those demos. I mean, I guess a lot of the demos that I showed in this particular video could well have been done with a computer sitting somewhere. But, for a lot of things that are portable or, or low power, you don't want to have your laptop tethered to it, to say nothing of the performance issues of sending data back and forth, as I discussed in the talk. So yeah, it's designed to encapsulate everything that an Arduino would do and everything that your laptop would do running audio software, just in one little self-contained block that ultimately, yeah.
Yeah, that's fantastic. That explains the pricing as well now.
Sure, yeah.
When I looked at the pricing, wow, that seems a little bit pricey, but now I understand why. This is really cool stuff with guaranteed quality of service. So that's
the idea. I mean, I mean, it's not designed just to replace a cheap Arduino board. It's designed to replace your computer, and so it's at the point that you want to do something 10 times, then having 10 computers is a bit of a limitation.
I can see you have to buy one now, so that's brilliant. Thank you.
Yeah, okay. I'm not actually here to sell things. I'm here to sell ideas. Let's say one of which is that this latency and detail kind of stuff really, really matters, and I think it's hard to communicate that over a video. But I think like with that Strummy instrument that I showed, for example, when you play it, there is something that happens that you somehow believe that these little lengths of string are actually making those sounds. And we've even had people in demos before say, "How did you tune them to be so precisely in tune?" It's like, it's actually all digital, but but the response is so tactile and it's so immediate that you could actually believe that the physical object is producing that sound. And until you kind of experience that, I think you kind of don't know what you're missing in the digital realm.
Yeah. I can now see all sorts of possibilities for sonification with this as well, because, sonification in the wild with Bela. Right, so that leads us on to the first question from Prithvi, who's asked a very ICAD related question. Prithvi says the low latency could potentially make Bela a very powerful as an interactive sonification platform. I'm curious about whether it can handle the typical chain of parameter mapping operations in real time, such as data preparation, transformation, for example, sigmoid, polarity, scaling, multidimensional mapping, and synthesis. Would you happen to have any experience with this sort of thing?
Yeah, absolutely. Great question. And the answer is yes, and yes. This is the kind of bread and butter of what a platform like Bela will do. As you saw in the talk, my background is coming from digital musical instruments, and parameter mapping is a really core part of a lot of instrument design as well, on all these same kinds of things: preparation, pre-processing, scaling, nonlinearity, various kinds of many-to-many relationships, and then of course audio synthesis. So you can do all that kind of stuff. I'd say that one thing that you can also do once your sensor data are signals, and they're signals of the same rate as audio, is you can start thinking about them a little bit differently as well, in a way that I think is kind of useful. Like, if you can apply higher low pass filters to them, you can be interested in the kind of the rate of change of something. You could be selecting for particular frequency components. You could be applying an FFT based process to do some sort of frequency detection, almost as if they were audio signals. And one of the things that I find as well, I mean, I could talk about mapping for the entire rest of this hour, and I won't punish you in that way, but there is, I think, so much more that you can do in an interactive system design context than what is the value of this input right now related to what is the value of this output right now. And I mean, I think that's probably, maybe that it goes without saying a little bit, but like, there is so much about interaction that I think is ultimately captured in the trajectory over time of signals. And I mean, that could be something as simple as just, doing a threshold to trigger something, but it can also be like, if you heard in that the demo with the e-textiles, I mean, there are these subtle sonic cues of plucking and tapping and stuff. And it's very hard to encapsulate that just in one immediate sample. There's so much detail of interaction to be had, and ultimately how to make any sense of that digitally is actually a really interesting and open question in my mind. But yeah, maybe just to wind it back, the short answer is yes, absolutely. Data mapping, parameter mapping is a thing that is very doable, and there are examples to do that, and happy to have a longer discussion about that at some point if you like.
Great. Because I'm not necessarily going to go through these questions in order, because there's one that Thomas Herman's just popped up that kind of fits well with what we've just been talking about. Thomas asks, he's curious as to whether there's a roadmap beyond the 1 gigahertz CPU for more complex processes.
Yes, absolutely. It's not something whose details I can really talk about right now, but we've been working with the beagleboard.org group, and there are already BeagleBone products that are faster than this 1 gigahertz CPU. For example, the BeagleBone AI, and we intend to and very much hope to be supporting these faster processors as they come out. We're very much aware of the kind of usefulness of not only faster processors but multi-core processors. So I can't I couldn't tell you precisely when and what kind of support that's going to look like, but yeah, it's absolutely on our radar screen. So stay tuned.
Excellent, great. Bobby Candy asks, how about using with Jack or something similar for interactive jamming? And Thomas mentions Jack Trip, which was discussed, I think, in a public seminar a couple of months back.
So we looked at this a little bit. It's actually sort of a complicated answer, because one thing is if you want to be using something like Jack, which is a process a different process running on the board. And certainly if you want to be using the network drivers, you're going to need to be using the Linux kernel. Now, the problem with that is that basically Bela gets its signature low latency by not using the kernel. So the idea is that your audio code needs to, at least the kind of core audio path, needs to be able to bypass all of the kernel infrastructure. So if you were reliant then on sending that through a whole IP stack or something that was running on the kernel, then you're going to have a bit of a problem, because you're going to end up losing all those privileges. I mean, you could also say, I suppose, in a sense, that the network latency is going to be by far the driving factor of something like that anyway. Now, that said, the other thing that I said in the talk that I think is really applicable here is that all the sources of latency add up. So if you've got a network latency of, I don't know, 10 milliseconds, let's say, and you could either add another 10 because of your audio devices, or you could add another 1. It's pretty clear what you'd rather do. So I think there might, there are possibly some ways that this kind of thing could be done. It definitely requires a little bit more design thought, and probably even a different hardware approach to Bela exactly as it is right now. But yeah, it's a great thought, and I think there's some possibilities there.
Yeah, I mean, I wonder if you could just use it for reducing the amount of latency in a networked audio system, because you're just using the hard real-time elements of Bela, and then you funnel it back into your IP architecture to broadcast it.
I mean, it's almost like what you would want in that way would be to have some kind of a hardware board that was doing the network broadcast that wasn't actually the Linux board, and that might be reasonably doable. I've not looked into it, but if you could have your network running at the same kind of hard real-time priority as your audio, then yes, absolutely, you could do that kind of thing. The trouble comes when your network is running at ordinary Linux privileges, and then the kernel's busy with something else, and then it ends up dropping packets and blah 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 blah.
Yeah. Cool. So Elias Elmqvist, that question just disappeared as I said.
Sorry, I was just...
No. Yeah. It just scrolled down. Yeah. If the audio would be synced with an interactive visual component, would there be a trade-off between syncing with the interaction of 1 milliseconds versus the video buffering 16.6 milliseconds for v-synced 60 frames per second?
Okay, that's an interesting question. There's several layers of answers there, I think. synchronizing with things is really important, and that's the whole kind of jitter argument. So if you could synchronize something directly with the video frames, 16.6 milliseconds, that's fantastic. That doesn't mean necessarily that your latency is going up, because the latency is the time between when your data comes in and when your data comes out. So when I say that we have 1 millisecond latency, it means that it doesn't mean that I'm sampling something every 1 millisecond. I might be sampling something every 22 microseconds, but it means that for it to kind of make its way through the little assembly line and then out the other side, that's 1 millisecond. So you could definitely align something very strongly with a video frame, and you could do that at very high precision, down to like a single audio sample, so it would happen 60 times per second, exactly aligned with the arrival of the video, and then you would have quite a responsive system. One thing that I think would be interesting about that from a technical perspective is how you actually do the synchronization, because well, you presumably want to, maybe you can get in some kind of digital signal that represents VSync. I mean, if you're doing it with VGA, then you've literally got a electrical line you could put into the Bela digital input, and it's actually really easy. But suppose that you were driving, suppose that you had a VGA signal that was coming out of your device, and you wanted to synchronize some audio with it, but your VGA signal was also going to an LCD monitor, let's say. One thing that is surprising but interesting is that LCD monitors have a lot of latency within them, actually. Like if you say go, it might be 100 milliseconds even in the worst case, but certainly could be very often 30 milliseconds, 50 milliseconds before you see that image pop up on the screen. And that's because there are layers of buffering. They buffer 1 or 2, 3 frames of video ahead of time. And you don't notice it because our eyes are not nearly as latency sensitive as our ears. But if you actually monitor the signal, it's a real issue. So I had a paper with a student in my lab where we were looking at the reaction time of violinists to some stimuli. And what we did was we put the stimulus up, and when the stimulus went up on the screen, we actually had a little black box that was in the corner of the monitor, and we had a light sensor on there that was going into Bela alongside the audio, so that you knew literally when that light hit the screen. And you could even see like the light at the top of the screen and the light at the bottom of the screen. They didn't move synchronously. So yeah, there's a whole bunch of interesting questions there, but yeah, long story short, yes, Bela is definitely capable of that kind of thing.
Cool. Thomas asks again, can a number of Belas be coupled to get n times 8 channels with the I/O? Sorry, can you couple n Belas to get n times 8 channels of I/O with the sample synchronized?
Not at the moment, but that's been kind of on my to-do list for, I mean, that's been on a like, oh, I think we ought to be able to do this for a lot of time. You could certainly run 8 Belas in parallel, and if they all have separate signals, they're going to be more or less aligned, but that's only more or less. They're running on different crystals. You ran them for a day, they would drift a little bit. It would be possible to do that kind of thing. And again, here's where the open sourceness of it comes in. You want to build that sort of stuff, great, and post on the forum will help you. But the way that you would do it is that there are some clock signals that actually run the audio codec. There's a frame clock, which basically goes every 44 kilohertz. And then there is a bit clock, which is some number of megahertz. And I guess what you would try to do is you would try to share those clocks, where you would have one Bela basically clocking all the other ones. And as long as that one started the clock and the other ones followed the same clock, then you could actually probably sample synchronize. It'll be a little complicated electrically, so that you don't have noise and reflections and stuff on this big long clock line, and you make sure everything starts at the same time. But in principle, that's the kind of thing that you ought to be able to do.
Maybe someone would build an external clock unit that you could plug a number of Belas into.
It'd be great. Yeah.
George Beringer wonders whether the latency optimization works the same on single-threaded audio engines like PD uses and on multi-threaded ones. Blocking is clear to me, but I find this threading concept confusing.
Yeah. Yes, it does. In fact, the kind of core audio process that runs is a single thread. And so we run PD on Bela. We run it using libpd, which is basically just a library, like kind of a graphics headless kind of library that just runs the PD patches on the board. And that what happens is it just runs with very small block sizes instead of a default of 64 or 128 or whatever. And so yeah, it's not actually the multi-threading that gets your audio code more efficient. In fact, yeah, because PD, as I think, as you know from the question, is a single-threaded environment, which is kind of annoying if you have if you have a computer with lots of CPU cores and you'd like to use them. I mean, maybe you can do that. Actually, I'm not really an expert on PD, but yes, yes, it'll work fine with single-threaded audio. And then what you would do is you could spawn extra threads if you wanted to do things like, like deal with some things in the Linux kernel that couldn't be as fast as audio, or if you wanted to do something like let's say you wanted to do a big, huge FFT every, 1024 samples. Well, you're never going to finish that within one tiny little audio block because it's a really long computation. But what you can do is you can offload it to a separate thread, and it can kind of churn its way through in the background while you're responding to much faster events in your audio callbacks. So yeah, threading is a thing you can do, but it's not dependent on threading.
Cool, thank you. Next question. Forgive me if I mangle your name, but Nicholas Rönnberg. Best Swedish I can do today. There were issues with the browser-based IDE and Chrome on Mac. Remembering trying it out at the autumn of 2019 without being able to connect the Bela to the computer, are such issues, quotes, history, end quote, now?
I mean, that would be famous last words. You could take it up with the Apple engineers for the next, Mac OS 12 or whatever is going to come out next. But yeah, I think the things that you're referring to have probably been addressed. The issue wasn't so much the browser itself; there's a virtual network device. So when you connect Bela to your computer, it does two things. One is that it looks like a storage device, but then the one that's more important is that it makes a network link between your computer and Bela over the USB port. And what had happened is that I think in Catalina or one of the Mac OS updates, they basically broke the drivers that we were using, and so you had to go back to installing your own drivers to get the network working, and it was not the optimal experience, let's say. But Giulio, who's our lead engineer, basically dug into this and came up with an amazing fix where he basically just discovered there was an entirely different class of drivers that you could run on Bela that was still supported on Catalina. So I think in the latest releases, you should find that it just plugs in and works. But yeah, that'd be the kind of thing where if you had a Bela and you were getting stuck with that, learn.bela.io, that's our kind of new resource for troubleshooting and tutorials and what have you. So just drop over there and you could probably find a lot, or go to the forum.
Cool, thank you. Arseni asks, is code inside the Bela, for example, Super Collider, transpiled to C++ or C? How in general can Bela work with those languages and systems?
Oh, great question. No, Super Collider actually runs as a process inside of Bela. So SC Synth will run connected to the Bela audio environment. So we have written some C++ code, because of course the synth is written in C++. We have written some code that instead of linking to Core Audio or ALSA or whatever, Super Collider runs using the Bela audio environment. And so it's actually, it's interpreting, and then so the synth is interpreting its node structure of synths, however it usually does. Now, Super Collider is an interesting case because the language and the synthesis are separated into two different processes. One thing that's kind of nifty about that is you can run the language on your computer, but the synth on the board. And what that means is that you have your convenient interface on your computer, but you still have the really low latency reactivity on Bela. If you were running PD, that runs with something called libpd, which again is just it's some sort of interpreted patch for your PD patches. The exception is there is a I think kind of open source community project called Heavy, which we were using very early in Bela, but still supported, where Heavy actually takes a PD patch and actually turns it into optimized C code that then you can compile and run on the board. The downside of this is that it supports a subset of PD objects, and sometimes the semantics are slightly different than PD in a way that you have to be careful about. But the upside of it is that you can get a lot more efficient performance compared to just running PD as normal. So yeah, you do have some different options for sure.
Brilliant, thank you. Well, that's super. We're just about out of time. So Andrew, thank you ever so much. That was, for me, a fabulous talk. And I think you've made, for me, the penny drop. And I can now see why I need to be looking at Bela and how it's going to help me as a sonification researcher to do more interesting things more easily. So that's great, and I hope that's been the case for other people here. As I said, Andrew isn't staying with us for the Q&A session, so please feel free to drop in questions in the Discord channel on the Discord keynote and panel thread. So thank you very much, Andrew, and I hope we'll see you again at ICAD soon.
Absolutely. Thank you so much for inviting me, and I hope to see you at another one soon.